Math 287, Quest to College. I'm Joe Vasta. We're going to do section 1.6. 1.6 is called linear differential equations of the first order. We did separable in 1.4 and now we're in 1.6. We are skipping 1.5 in this class. So we're going to do something kind of weird before we get into this. We're going to let p of x be a function. We're going to ask the question, is there a function I of x such that I prime equals I times p? And the answer to that is yes. You can pause the video and see if you can figure it out. This is a bit theoretical. The answer, I of x equals, not really obvious, e raised to the integral p of x dx. So let's go ahead and check our answer. If we check our answer, we're going to go ahead and take the derivative of I of x. The derivative, we're going to do the chain rule. Derivative of e to something is e to something. And then now we're going to go ahead and do the derivative of something. The derivative of the integral happens to be p of x. This first part right here, e to the integral of that, is really I of x times p of x. So on the next page, and in fact throughout 1.6, we're going to use this fact that the answer to this is e raised to the integral p of x dx. This is called the integrating factor. So that is the method of solving linear differential equations of the first order. It's called the method of the integrating factor. Let's go ahead and talk about what a linear differential equation is when it's first order. Well, what a linear differential equation is, of first order, is here is the y prime and here's the y. They are not raised to powers. They're not multiplied by each other. They're not the arguments of functions like the sine or the log. It looks like this. If you look at your 1.1, 1.2, 1.3 notes, we had a linear differential equation that was nth order written down. Okay, now when we solve these, what we want, we don't really want this function of x in front of the y prime. So I'm going to divide everything by this function of x. What we want for this method to work is just the y prime by itself. So a naught of x over a 1 of x, we're just going to call that p of x. And then g of x over a1 of x, we'll call that f of x. So this is the form that we want when we do the method of the integrating factor. I'm going to go ahead and rewrite this so it doesn't say p of x, but we're going to remember that p is a function of x, and so is y, by the way. And this equals f. So what the method of the integrating factor is we are going to look for the integrating factor of p. The integrating factor of p, we said, was this function called I. So I'm going to multiply both sides of this equation by I. So I have I y prime plus I p y equals I times f, if. Okay, now, because we have this integrating factor, so I is the integrating factor, and if you look at the last page, it has the property where I prime equals I times p. Now look what we have here. We have IP. So we're going to replace that with an I prime. So I have I times y prime plus IP is I prime times y. This is if. Little iffy here. And so the orange got replaced with the orange. Now, stare at the left-hand side. You might have to pause the video to think about this, but what does that remind you of? Well, what it reminds some people of is the results of the product rule. We have, I usually do it this way, the derivative of the first times the second plus the first times the derivative of the second. This equals I times f. And so that's the magic of the integrating factor. It's not really magic, it's math, is the fact that now we get something that looks like this. This will happen on every problem. And then what you'll be able to do on both sides is integrate both sides. And you'll see that I times y equals the integral of if of I times f. And then, of course, you would divide by I. Some teachers actually will do all the problems just plugging it into a formula. I'm going to actually work out some of the problems this way so you can see the method work a few times. So let's go ahead and do problem number 1. This, was pretty theoretical, but it kind of explains how the integrating factor works in a more general setting. Let's do a specific setting here. And I have this differential equation right here. So I'm going to identify a few things. This guy right here is function p. And this guy right here is function f. And the first thing that I want to note is that p and f are both continuous for all real numbers, from negative infinity to infinity. Okay, now that's going to help out. Maybe not in this problem. You might not see the worth of this, but we'll continue to do this. So this differential equation that I wrote up here, I should have actually said this first. This differential equation is not separable, because if you solve for y prime, you'll have on the right hand side e to the x squared plus 2xy, and there's no way you can separate the x's and y's using multiplication. So this is a differential equation that we could not do until this section. Okay, the integrating factor, that's the next thing I want to do. The integrating factor is going to be e, and then we raise it to the power, go e to the power of, and then you put p of x in there. So this is negative 2x dx. Okay, so what is the integral of negative 2x? Well, it's negative x squared. E to the negative x squared. There's also a plus c. Okay? Now, in the future, when we do the next problem, we want to take, I don't know why I'm using the word take, but take c to equal 0. And that's going to make your life a lot easier. But right now, I'll keep it in here to show you why, maybe this will work. Remember that this is really, the integrating factor is really e to the negative x squared, and then we have e to the c. Okay, so we'll write that. So what did it say? If you remember the derivation, we're going to multiply this differential equation by this integrating factor. So I have e to the negative x squared times e to the c. I know I can write that as another constant. This is going to be multiplied on both sides. Now this integrating factor will only work if there is a 1 in front of that y prime. If there's not, you can divide out. Like if there was an x there, you would divide everything by x at the beginning. Now, do you see that e to the c is just some number? And we could divide both sides of the equation by e to the c and you don't even see it. So that's why we're telling you in these problems to take c equal to 0, because it's not even going to show up. So I'm going to go ahead and say we don't even need this. Let's go ahead and do the multiplication. When we do the multiplication, we end up getting e to the negative x squared y prime minus 2x e to the negative x squared y. This equals e to the negative x squared times e to the x squared. So on the left-hand side, what I end up getting, this will always happen. I end up getting the derivative of the product, and the product will always be y times the integrating factor. And I'll always write it like that. And now if you're like going, what just happened there? Well, let's work backwards. Let's do the product rule. The derivative of the first, which is that, times the second, plus the first, which is right here, and that doesn't say plus there, but it will. We'll see that. Plus the first times the derivative of this. The derivative of e to the negative x squared is e to the negative x squared times the derivative of that, which is the negative 2x. So basically we are doing the product rule of derivatives backwards when we do this. Now on the right-hand side, we multiply that together by adding the exponents. We end up just getting a 1. Okay, so the next step that we're going to do is we're going to integrate both sides with respect to x. And don't you see on the left-hand side, you are just going to have y times our integrating factor. And on the right-hand side, well, this is where we have to integrate something. Ooh, the integral of 1 is x, and then we put plus c, and that's the c from both sides. We're almost done with this problem. We have to solve for y now. So I'm going to write this as y equals x plus c divided by e to the negative x squared. We can actually make it look a little better because this is a negative exponent. We'll just bring it up, and this is going to be e to the x squared times quantity x plus c. And that is our answer. This is the method of the integrating factor. So I think for us to feel comfortable with this, we should look at a few more examples. Example number 2 looks like this. Y prime plus 1 over x times y equals 0. The first thing I do, and you can look at the last problem, I circled this, I identify this as P, and I identify the thing on the right-hand side as F. So that's what I'm doing here. And the last time I said P and F are both continuous on all real numbers, but P actually has a problem there at 0. So P and F are continuous. So I'm solving this differential equation. We're solving it on intervals. These guys are going to be continuous on, you have to pick a side. You want to go from 0 to infinity or from negative infinity to 0, but you cannot cross the 0. So I'm going to pick the biggest interval, and they're both equally big in this case. So I'm going to say they're continuous on 0 to infinity, and that's where I'm going to solve this differential equation. The next step that I want to do is compute the integrating factor. Now, there is a 1 in front of the y prime, so we're good with that. The integrating factor is going to be e raised to the integral of 1 over x dx. So what is the integral of 1 over x? So you have to remember back to integration. It's actually the ln of the absolute value of x. And we're going to actually take our c to be 0, because we saw in the last problem we can do that. So e to the ln absolute value x, by properties of logs, that thing goes pop, and you end up just getting the absolute value of x. Now here's the great part. Since we're solving this on the interval 0 to infinity, absolute value of x well, x is always going to be positive, we can just write the integrating factor as an x. Okay, the next step is taking our differential equation, multiplying both sides by the integrating factor. When I do that, I get xy prime plus y equals 0. Now, because of the magic of the integrating factor, this guy right here is the result of the product rule, and it will always be the same thing. The product rule of y times the integrating factor. And I know that's not alphabetical, but it's the way that I like to do it, because I'm going to check this. Let's do the derivative of this product. The derivative of the first times the second, plus the first times the derivative of x with respect to x is 1, and so this gives us something that's true. What was the next thing that we did in the last problem? We integrated both sides with respect to x. Now the integral of a derivative, so it's like putting the derivative gun and the antiderivative gun right next to each other so they kind of neutralize. Of course, you would still get a plus c, but I'm going to put that on the right-hand side. What is the integral of 0? Well, the integral of 0 is 0 plus c, so here we have that right there. And y equals c over x. There is our solution to this, the method of the integrating factor. The funny part about this is our original differential equation, this guy right here, was both linear and something that we didn't point out at the beginning, this is also separable. So maybe as an exercise on your own, you could write this as y prime equals negative y over x, and this is dy dx. You can solve this. You'll end up getting the same answer, and I would encourage you to do that. Let's go ahead and do problem number 3. And maybe you want to tackle problem number 3 on your own, so you can pause the video and do that. Okay, so problem number 3, we don't have a 1 in front of that y prime, so I'm going to go ahead and divide everything in the equation by the x squared plus 1. At the same time, this guy does not have a y in it, I'm going to put him on the right side. So I'm going to do 2 steps in 1. Y prime plus 3x over x squared plus 1. There's a y right there. This is going to equal 6x over x squared plus 1. Okay, so now what do I have? I have a 1 right there. That's what I want. The method will work. And I'm going to identify this as function p, and this guy right here as function f. And I notice that these guys are continuous for all real numbers. See, there's an x squared plus 1 there. P and f continuous on the interval negative infinity to infinity. So now it's time to find the integrating factor. The integrating factor is going to be e, I'm leaving some space here, and then we take that to the power of the integral 3x over x squared plus 1 dx. Okay, so basically on another piece of paper, I'm going to go ahead and do this. 3x all over x squared plus 1 dx. And then we'll come back to the problem. So you've probably been taught when you do an integral like this to do a u substitution, and there's nothing wrong with that. U equals x squared plus 1 du equals 2x dx. X dx equals du over 2. And then you were taught that maybe you go like this. You put the 3 out front, you have an x dx right there, so you can replace that with a du over 2, and then you have an x squared plus 1, so that's u. So this is 3/2 integral du over u, 3/2 ln absolute value u plus c. Okay, so there's the answer. We can go back to the other page and put it down there. Okay, so another way you can do this is you can look at the bottom and say, oh, look, the derivative of the bottom is 2x, and I have a 3x on the top. So I'm going to go ahead and pull that 3 out front, and I'm going to put a 2 right up on top. Now I have to pay the price, balance the books by putting a 1/2 out front. And so what I see is we have a x squared plus 1, its derivative, 2x is on the top, which means I am now taking the antiderivative of something over, or we can actually see this 2x, we have its derivative and the thing on the bottom. So it's kind of like a 1 over u. So I have ln absolute value of x squared plus 1 and then plus c. Now over here I forgot to actually put ln x squared plus 1. So what is happening here is we're doing, when we do use substitutions like this, we're doing something called the reverse chain rule. The chain rule says you take the derivative of ln something, which is 1 over something, and then you actually do the derivative of that something, which is 2x. When we do the reverse chain rule, we have to have the derivative right next to the dx, and that derivative actually disappears. You know, like going from here to here, the derivative appears, and going here back to here, that derivative 2x disappears. And so when I do problems here in lecture, I will actually eyeball this when I do the use substitution. So let's get back to our problem here, where we have, so we went ahead and computed this. This is e raised to the 3/2 ln absolute value x squared plus 1, and we can leave the c off, and so that's what we have. Now I can't make the e and the ln disappear with the properties of logs because there's this 3/2 there, but I can use the power rule for logs and make that 3/2 power jump up here. So 3/2. Now this thing goes pop, and I end up having x squared plus 1, the absolute value, to the 3/2 power. Now, this x squared plus 1 is always going to be positive, so we really don't need the absolute values there. We can just replace those with regular parentheses. Okay, so now we have just found what the integrating factor is. The integrating factor is x squared plus 1 to the 3/2. I'm going to go ahead and multiply. This is the equation I'm looking at. I'm going to multiply the equation by the integrating factor. And when I end up doing that, I end up getting x squared plus 1 to the 3/2 times y prime. And then I have plus x squared plus 1 to the 3/2 times this middle term. So the thing that I'm circled, that's what I'm multiplying this by. And so I have 3x x squared plus 1 y. This equals, oh boy, x squared plus 1 to the 3/2 power, and then we have 6x over x squared plus 1. So let's go ahead and rewrite this nicely. So it says x squared plus 1 to the 3/2 power times y prime, plus we have 1 on the bottom and 3/2 on the top. This is going to give me 3x times x squared plus 1 to the 1/2 power. This equals 6x, then we times x squared plus 1 to the 1/2 power. Now the whole idea of this is some of you may have decided, if you've done a few of these problems, to skip some steps. This left-hand side will always boil down to the derivative of y times the integrating factor. Will always happen. So I've seen people, and I've been known to do this, so once I get this and I start multiplying left and right hand side by the integrating factor, I'll just jump right to this. Okay, there's a risk in doing that, and if, you know, I mean, right here we can kind of see where things are coming from. Watch this. The derivative of the first times the second plus the first. So I forgot to put something. What did I forget to put? The y here. Okay, so the derivative of the first times the second plus the first, there's the y there that I just put there, times the derivative of the second. The derivative of this is 3/2 this to the 1/2 power, so we have that to the 1/2 power, and then 2x. So the 2 on the bottom of the 3/2 and the 2 are going to cancel, and you'll end up getting that as the derivative. This equals 6x, you know, the right-hand side I'll just keep the same for now. So what am I going to be doing? I'm going to be integrating with respect to x on both sides. So I need another piece of paper. So I've just hit the tripod, got to make sure, oh yeah. Hopefully it's been straight for this, but I don't know. Oh wait, maybe not. I'm messing this up here. How's the clarity? Still pretty good. Okay. So what I'm going to do is I'm going to go ahead and put that right there. Going to write the left-hand side. We have the antiderivative gun and the derivative gun, so they kind of neutralize each other. We're going to write this as y x squared plus 1 to the 3/2 power, so that's y times the integrating factor, equals, well now look what I have to do over here. I have to do the integral of this. I'm going to go ahead and use that eyeball method, and I'm going to say, look at this. I have this right here, x squared plus 1. The derivative of that is 2x. That's what I would let my u equal to. So do I have a 2x right outside? I have a 6x, and I'm going to break that 6 into 2 times 3. By doing that, now this 2x is going to disappear, and I'm just doing the antiderivative of u to the 1/2 power, which is really this u, what we would have called u, to the 3/2 power, and then we have the 2/3. And we have to put our plus c. So what we have is the following. We have y times x squared plus 1 to the 3/2 power equals 2 x squared plus 1 to the 3/2 power plus c. I'm going to divide everything in this equation by x squared plus 1 to the 3/2 power. So this is going to give me y equals 2, because those are going to cancel, plus c over x squared plus 1 to the 3/2 power. And that solves the differential equation. You know, some books might write the answer like this. C, we have x squared plus 1 to the negative 3/2 power. Okay, so some, that's acceptable as well. So that completes problem number 3. Let's go ahead and look at problem number 4, which is an initial value problem. Which looks like that. It's the same problem that we just did. So here is the answer. That is, hopefully that was the thing that I just wrote down. Yep. And now we have the point 0, 5 that we're going to plug into this general solution to get a particular solution. So y is 5. This equals 2 plus c. X is 0, so this is 1 to the negative 3/2 power, which is 1. So c is going to equal 3. So our answer to this one would be 2 plus 3 times x squared plus 1 to the negative 3/2 power. So that is the answer to the initial value problem. So at this point, we're pretty much done with this lecture. So for those of you who are like, yep, I'm sick of hearing this guy on YouTube, then please turn off the video. We're done with 1.6. But this is just a bonus problem. I didn't think I would have time to do it, but I'm going to do it because it has trigonometry in there, and we do understand that trigonometry can be deadly for some people. So here is a linear differential equation. We do not have a 1 there, so I'm going to divide everything in this equation by sine x. So I have y prime minus, this is going to be the cosine over the sine, and then we have, that's going to be times y, and then this is sine 2x all over the sine x. Okay, the first thing to realize is you can write the cosine over the sine as the cotangent if you want. We can keep it this way or write the cotangent. But over here, what we have is sine 2x over sine x. Now, I'm not going to, like identities, this is one where a lot of people forget, but the sine of 2x is actually 2 cosine x sine x. And we have that over the sine x. So that's what we have right there. So the sine x's cancel, and so the right-hand side is going to give me 2 cosine x. I'm going to go ahead and change, I don't know if I want to change that. Do we want to change that? No, I'll just keep it as the sine over the cosine. Or the cosine over the sine, whatever that was written there. Okay, so the next problem is identify. There's the value of p, or the function p, and then this is the function f. There is a 1 in front of the y prime, so we're ready to figure out what the integrating factor is. The integrating factor is e raised to the integral negative cosine x over the sine x. And this is dx. So that's what we have there. To do this integral, I say, well, what is the derivative of the bottom? The derivative of sine x is cosine x, so that's right up on the top. The cosine x will disappear. I'll have negative ln absolute value sine x, and c is 0. The one thing we didn't write out is about p and f. They are continuous. Well, f is continuous for all real numbers. Sine, we don't want that to be 0, so we're going to say this is continuous from 0 to pi. So think of the sine graph. If sine of 0 is 0, we don't want that, and sine of pi is 0. Okay, now we could have also been looking at the cotangent and analyzing it the same way. So because we have 0 to pi, and sine is always positive there, this we can rewrite without the absolute values. I'm going to take this -1 and put it up for the exponent. So this is e to the ln sine x. There's a -1 there. That part right there goes pop. And we end up getting sine x to the -1. It's not the inverse sine. This is really 1 over sine x. Which, if you like, you can write that as the cosecant of x. So this is what I'm going to multiply my differential equation by. I'm going to multiply it by the cosecant. So here's y prime minus cosine x over sine x times y. This equals 2 cosine x, and I'm going to multiply this whole equation by the integrating factor of the cosecant of x. And if it helps, maybe you can multiply by 1 over sine x if that helps things out. So this is what I'm talking about, where you can skip a few steps. And I don't know if I should do that here, maybe. I mean, I can write out the left-hand side and then verify that it is the result of the product rule, reverse product rule. But what's going to happen on, I'm saying the right-hand side, the left-hand side. What's going to happen on the left-hand side is you will get d dx of y times the integrating factor. It's the right-hand side that I have to worry about, and the right-hand side is cosecant and cosine. So this is 2 cosine x cosecant x. And so that's what I have. So, you know, like, we always write this part down on the left-hand side. I'm not going to write it down because the same thing happens every time. It's always going to be y times the integrating factor, the derivative of that. Okay, the right-hand side is going to be different in each problem, and the integrating factor will be different. On the right-hand side, because I know I'm going to have to integrate this, I'm going to write this as 2 cosine x over the sine of x, because the cosecant is 1 over sine x. And we still have d dx y cosecant x. Okay, now I'm going to go ahead and integrate both sides. And I end up getting y times the cosecant x. This equals, we kind of did this before. I have the sine on the bottom and its derivative on the top. I'm integrating with respect to x. So I'm going to go ahead and write this as 2 times the ln absolute value sine, but we're doing this from 0 to pi. So I don't need the absolute values on the sines. This is sine x plus c. And that's what we have so far. The cosecant is really 1 over the sine. So you can multiply or divide by the cosecant or multiply by sine. You end up getting y equals 2 sine x. We have the ln of the sine x plus c. Now, in this problem, they asked this initial condition, y of pi halves equals 2, y of pi halves equals 2, and so we're going to figure out what the c is and write a particular solution here. So we have 2 equals 2 times the sine of pi halves, so sine of pi halves, I'll just write this in here. We'll figure that out on the next thing. This is ln, the sine of pi halves, and we have plus c. The sine of pi halves, that's where, you know, sine goes up and then it goes down, so that's going to be a 1 there. These guys right here are 1s. So this gives me 2 equals 2 times 1, and then we have in here The ln of 1 is 0 plus c. 2 equals 2c. c equals 1. So now we can go up to this equation, replace the c with a 1, and that will be our final answer. Y equals 2 sine x. The ln sine x plus 1. And that gives us the answer to this bonus problem number 5, which I wasn't going to do. I'll see you next time.